Morning, everybody, and thank you for joining us today for another delivery of how to select and design a commercial heat pump water heating system. My name is Armando Berdiel, Technical Development Supervisor with Lighting Design Lab, part of Seattle City Light. I'm very happy to have here Lauren Bhaskar with DNR International and Evan Green with Ecotope. Talk about water heaters, heat pump water heaters. This is a great, relevant topic today. Yesterday, we had a why these water heaters are relevant. Today, we're going to get a little bit more into the how. So without further ado, take it away, Lauren.
Thanks so much, Armando. What a pleasure it is to be here with Seattle City Light and the Lighting Design Lab and our colleagues at Ecotope, Evan Green being here with us. We've really enjoyed working with the Ecotope team to develop these series of educational modules on commercial heat pump water heating systems. So super happy to be here, and thanks to everybody for joining us. Evan, you want to move ahead and we'll do a quick before we begin. So everyone's muted on this webinar, unfortunately, right? But we do love to hear your questions and comments and your wonderings as the session unfolds. So on your go-to menu, you'll see that there's a chat feature. Feel free to enter questions, comments, wonderings in that chat feature, and I'll make sure that I'm going to turn my camera on, Evan, to let you know that we've got those questions, and then you'll know you can pause at an appropriate time and we can interface together to figure out how to answer those. So that'll be the way we do things. The other thing is to have your smartphone handy because we're going to be launching an app called Slido, which allows us to ask you information. It doesn't collect any of your data, doesn't send you any spam, so very clean and safe. But we'll do that here in just a bit. So have your cell phone handy. Also, in the handouts tab, you'll see that there is the participant handout that goes with today's presentation. You can download that and keep it for yourself or write notes on it as we go, as you wish. But that's for you to take away today from this session. All right, Evan, so excited to have you here. You might introduce yourself a little bit, but take it away, sir. Thank you.
Yeah, thanks a lot, Lauren. Yeah, my name's Evan Green, and I'm a research engineer at Ecotope, an engineering firm in Seattle that's focused on designing efficient buildings that are solely ran off of electricity and don't use any natural gas, as well as working with manufacturers to research new technologies to drive the design of these highly efficient buildings forward. So today we'll be focusing on one of the technologies that Ecotope has really put a lot of work into, and that will be commercial heat pump water heaters. So the first thing we'll do today is we'll use that Slido app that Lauren was talking about, and you can use your smartphone, and if you have an iPhone, you can even just scan this QR code in the corner of the screen here, and it'll open up a Slido survey. So this will be a good way for me to get a lot of feedback from you guys on first of all, where you guys are calling in from today and what your occupation is and your familiarity with heat pump water heaters. So then I can possibly tailor a little bit more fine-tuned into what you're looking for here. So I'll give you a second to get onto the Slido app and answer some questions before we dive into the first question.
So Evan, as folks are responding, you didn't always work at Ecotope, right? You came from another entity. You want to tell a little bit about that?
Yeah, that's right. I had a pretty special learning ground going into Ecotope that gave me kind of a head up to start working with this technology. And so I worked for a manufacturer in Eastern Washington, Colmac Water Heat. They're a pretty large heat pump water heater manufacturer that sells larger commercial heat pump water heaters. And so they were one of the first back in the 80s to implement these systems in Hawaii, where they were the fuel was really expensive there. So they were looking for a good energy efficient solution. And the heat pumps worked amazingly there. So that's kind of where I learned all my baseline knowledge about heat pumps. And then I was able to expand that through Ecotope and think about the specific designs that might cater to some of the other specialties that other heat pump manufacturers require.
Yeah, awesome. And we've gotten so much from you in terms of all the expertise you brought. So it's been super fun to work with you, Evan, and really appreciate that expertise you bring. Awesome.
Oh yeah, and TNR has done a great job in bringing out all this information, because us as engineers, we might not be the best at figuring out how to best share the knowledge, but DNR has been great at, teasing that out and being able to format it in a way that people can actually digest. So it's been great working with Lauren and the rest of the team. So some occupations we're seeing today, we have a building systems manager, architect, small business outreach. That's really great. Electrification, market transformation. That's perfect. Yeah, you're in the right spot today. And we have an engineer and energy management analyst. So great. Yeah, the heat pump water heaters are going to be a big topic in all of these fields. So that they're perfectly justified why you're here today. So a good majority of people are a little familiar with heat pump water heaters. So that's good. Some of this might be a little bit of review, but I'm hoping today to really bring some high level knowledge and help you figure out really what you need to look at to dive more deeply into considering heat pump water heaters, whether you're a designer or you're looking at policy, or you want to implement heat pump water heaters into an energy efficient plan for your building. And then some people have never heard from them. There will be a lot of really great information here for you as well. So our main objectives today are going to be to look at the building types and applications that these heat pumps can be installed in, as well as the different components within a commercial heat pump water heating system and how that might compare to something you're a little more used to. And then we'll look at the key design considerations. And I'll remind you that this is just an hour session, so you wouldn't look to this presentation for everything you need to consider with heat pump water heaters. But it'll be a great start to figure out where to look. And then we'll talk about some Seattle code updates, since we are working with the Seattle City Light for this. So there's potentially a lot of people from Seattle that are going to be interested in the code specifically. So the first thing we'll think about is the building types and applications. And really, heat pump water heaters have been proven to work in every type of building. So I'll use residential as a first example. Residential heat pump water heaters are something you can just go down to Home Depot and buy and replace your electric water heater, maybe put in your basement in your garage. But today we'll be focusing on the commercial heat pump water heater systems, which are maybe a little less known about. You're not just going to go to a big box store and buy one, but they're still as efficient and as effective as the well-tuned residential heaters that have been marketed for a while now. So where we've seen the most applications so far with heat pumps is going to be in the residential sector. And this is a huge market opportunity in Seattle and really every other big city and small towns alike, because we can put smaller commercial systems in these low-rise apartment buildings, as well as larger commercial systems in the mid-rise buildings around 7 floors, which we see a lot of those in Seattle. And then the high-rise buildings work well with heat pumps as well. And you'll see big systems of several large commercial heat pump water heaters that can serve the domestic hot water needs of these high-rise buildings. Really, there's not a limit on how much hot water they can supply. It's just a matter of getting more heat pumps on the roof of your building or wherever you can fit them. And then even though they're more recognized in residential right now, there are many other ideal installations for heat pump water heaters. Really, any building that needs hot water can benefit from a heat pump water heater. And the commercial size systems are often in a centralized heating plant, like you would see a central boiler plant in a mechanical room in a lot of these buildings. But it doesn't have to be. You can have smaller integrated heat pump water heaters distributed throughout the building. Say if you have a library with a set of bathrooms in the corner, you might not have a central hot water system. You might just have a heat pump serving those bathrooms in the library, and then maybe there's another building attached to it that has a separate heat pump. And so the components of a commercial heat pump water heating system, they're all components that you'll be pretty familiar with. They just interact in a pretty specific way. And I want you to keep in mind that all of these components are helping the heat pump operate more efficiently and reliably. So if you're designing a system or looking at a system like this, that's the frame of mind you need to be in, is how are these different components helping the heat pump operate to make reliable and efficient hot water. So there's going to be 4 components we talk about today. And the first, of course, is going to be the primary heat pump water heater. So this is the star of the show, and it's heating the cold water from the city up to a point that can be used for showers or washing your hands or really anything you need hot water for. So that's going to be the primary focus here. And then the primary storage is what is paired with this heat pump water heater. And the storage offers hot water storage, of course, but there's a couple of auxiliary functions that we'll go over that really help it be more in tune with the heat pump water heater to efficiently heat this water. And then something you might be a little less familiar with is the temperature maintenance system. This is a little bit newer of a concept compared to the design of a conventional gas system, but it's serving a purpose that has always needed to be served in these larger buildings, which is keeping the water in the distribution loop hot. Because if nobody's using water at the fixtures, then all of the hot water in that plumbing that's waiting to be used is just going to cool down. So that needs to be circulated and reheated with this temperature maintenance system. And then we have the controls, which are the brain for the whole system. And these are extremely important as well because they tell the heat pumps when to turn on and off, which is really important because you need to make sure the heat pumps are turning on at the right time and not running at a time that could damage the heat pumps, or not staying off in a time where you might supply cold water to the building. So now we're looking at kind of a cartoon version of one of these integrated heat pumps you'll find at Home Depot that's more recognized in a residential setting. You might have one in your closet or your garage. So we'll see how this compares to all the components in that larger commercial system we were just talking about. So first of all, we have this compressor and fan and some refrigeration components on top. That's going to be the heat pump water heater that's actually pulling the heat out of the air around it and putting it in the hot water you're going to use in your building. And then connected to that is the primary storage that's storing this hot water and allowing the heat pump to connect to something to actually heat, so it doesn't have to work as an instantaneous heater, and it has this buffer supply and storage of hot water whenever it's needed. And this tank's just built right into your integrated heater as one package. And then we have the temperature maintenance system. And in a residential heater, sometimes you won't even have this if you don't have a circulated water system. But on some larger integrated heaters, you'll just see it as that return pipe going back into the bottom of the tank. So we don't have a fully separate heating system, but they've thought about this, and it's still a big primary function of this integrated heater. And then the controls are what's telling this heat pump to turn on and off. When the water gets too cold, it's going to tell the heat pump to turn on until it's warmed all the way back up and shut back off. And then there's some auxiliary functions that can provide as well, like alarming and reporting and even load shifting. So now we can dive a little bit more deeply into the heat pump water heater itself. And to do that, we can talk about how the heat pump actually works. So I'm going to be talking about refrigerant pressures and temperatures, but the biggest thing you need to remember is these heat pumps are not creating heat with electricity. All they're doing is they're moving heat using the refrigerant cycle inside of them. So they're harvesting heat from the air around it, and they're moving that into the hot water. So that's why they can work so efficiently, is because they don't have to make this heat. They're just using the air, the source around it, to collect it efficiently. So how do they do this though? You're talking about, in some situations, there's 10-degree air that you're moving heat out of and into 150-degree water. And the second law of thermodynamics tells us that we can only move heat from hot to cold. You're not gonna put an ice cube in a cup of water and actually cool that ice cube down. So to think about how this happens, we need to think about how the heat pump manipulates different pressures in the system. So if you draw a line right down the middle of this refrigeration circuit here, you can draw it between the compressor and the expansion valve. So what's happening here is the compressor takes this refrigerant and it pumps it into the high pressure side of the system. And then this expansion valve holds most of the refrigerant there. So the compressor is just pressurizing this loop on the right side. It's pulling refrigerant from the left side. So at the same time you get high pressure on the right, it's pulling refrigerant out of the left and causing really low pressure. And then this expansion valve is balancing the whole process to be able to tune in how high this pressure really gets and how low this pressure gets. So we have a high pressure side and a low pressure side. And that's important because when you change the pressure of a gas, you're also changing the temperature. So if you think of, maybe you've cleaned your keyboard off with a can of dust off, by the time you're done using that can, it's ice cold because the pressure inside that can has dropped down to a point that has lowered the temperature of the entire can. I went paintballing as a kid, and the same thing happened in my CO2 tank. It ran out of pressure, so it got extremely cold. So the same thing's happening here. When you drop the pressure on this side, you have a really cold half of the loop, while you raise the pressure on this side and make it really hot. So now, if you have a really cold half of the loop here, and now you have an air coil on this half of the loop, you can pass relatively cool air over that coil, and now that air is actually warmer than that cold side of the loop. So it's that half of the loop is sucking heat out of that air, and now that heat can be used in the system. So now, since this refrigerant is slowly circulating through this loop, we have this slightly warmed refrigerant that was initially really cold because of the drop in pressure. And now that's transferring to the high pressure side, where it's pressurized and raises that temperature really high. So now the hot side of the loop can now transfer that heat into domestic hot water. So we've pressurized this loop to the point where the refrigerant might be 160 degrees. So you can heat this water up to a really high temperature with heat that you have pulled out of this really cold air. And the only thing we're paying for here is the work done by this compressor, which is a lot less power than, it's a lot less energy than the actual heat that's being transferred into the water. So we might have paid for 1 kilowatt of compressor power, but now we're getting 3 kilowatts of heating into the water. So you're paying for 1 kilowatt, you're getting 3 kilowatts, where an electric resistance heater, where you would have used electricity to actually make that heat, you're paying for 1 kilowatt and you might get 0.9 kilowatts of heating into the water. So that's a really important piece here, is the heat pump is just moving the heat, so we don't have to pay nearly as much for that heat to get put into the water. And there's two main ways that the heat pump's going to interact with the tank to heat this water and store it. So the first we call a single pass heating cycle. So it's going to take really cold city water and it's going to trickle it through the heat pump and allow that water enough time to heat up to a specific temperature. A lot of times that'll be 140 to 150 degrees. So we have a pump and a valve in here that flows just enough water through, allows it the time to heat up to 140. and now it's going to eject that into the top of this storage tank, where now we have this big massive hot water in the top, while the cold water sits on the bottom waiting to be heated by the heat pump. So that's kind of special and specific to heat pump water heaters, while a conventional gas heating system would be more like the multi-pass cycle, where you have more uncontrolled flow through the heater. So the water only has time to heat up to maybe 10 to 15 degrees warmer. So you're going to be operating in 130 to 140 degree range in this whole cycle, which means this warmer water is going to be a lot harder to push that heat into. So the heat pump's going to have to work harder to move that heat into the water, meaning it's not going to work as efficiently. So generally, single pass heat pumps are going to work a lot more efficiently than multi-pass heat pumps, and they're not going to have to raise that pressure as high because they don't have to move that heat into such a hot fluid. So now we can look at the storage that's interacting with this heat pump and what benefits it might serve. So you can think of your hot water storage in a domestic hot water system kind of like a battery bank, right? So the storage itself is what's going to be handling anytime, say you have all of your occupants in a building just all turning on their shower at once in the morning to get ready for work. Now they need really high amounts of hot water that your heat pump might not be able to provide right away, but your storage is able to store enough hot water to handle that peak load. And then your heat pump's acting like a trickle charger and just recharging that storage throughout the day. So anytime there's a big peak, the storage can send as much hot water out as it needs, while the heat pump just slowly recharges that. And that also allows the heat pump to run for a much longer period, which is a lot easier on heat pumps because the longer they run, the more efficiently and reliably they can run, because they've kind of settled into this heating cycle, and it's a lot harder for it to raise in temperature if it turns on and off really frequently.
Hi, Evan. Interesting discussion, because I think what you're saying is you're trading off the amount of primary storage for the fact that the heat pump takes longer to heat, correct? So we had a comment, which I thought was really interesting, and I'd like you to speak to it just a little bit, and that was about, is there a possibility for tankless commercial heat pump water heating? In other words, trying to reduce standby losses in the primary tank, but how do you generate enough hot water to meet the building demand? You know, that's kind of the quandary.
Yeah, so there's been a lot of success in tankless gas heating, mostly because with gas heaters, it's really easy to ramp up to a really high BTU content for small amounts of money. You're just shoving more gas into the system, burn a hotter flame, heat to as much as you need. But with heat pumps, since you're harvesting it from the air, that really high peak load that you're trying to satisfy, if you pick a heat pump that's able to match that load, you're going to be paying a lot more because it has to actually collect that heat from the air, right? So your heat pump's going to be much larger, and at the same time, your heat pump's going to have to ramp up and down really quickly, which just with the physics of what it's doing to the refrigerant behind the scenes is not going to work efficiently, and it's not going to end up in a reliable heat pump. So you want to be able to basically operate your heat pump at a really low rate throughout the day while your storage handles these peak loads. And there will be more losses, but they'll be more than offset by your heat pump working more efficiently than an electric resistance or a gas heater.
Yeah, it's kind of the inverse of a gas situation, right?
Right. Yeah.
Right. Thank you.
Yeah, and we'll talk a little bit more about it in sizing. So I talked about how in a single pass system, the heat pump ejects hot water to the top of this tank, and that's really important. And we call this, there's a term for it, it's stratification. So the hot water sits on top, the cold water sits on bottom, and then there's a small layer between the hot and cold that separates it really well. And we want to maintain this because the colder the water entering the heat pump in a single pass system, the more efficiently it will heat, because it's easy to shove that heat in there. So that's why we have a dedicated temperature maintenance system is because we don't want this hot water return coming back to the tank in a way that mixes this stratification up. So a better stratified tank is going to make for a much more efficient heat pump. And I can pause for questions here. I've gone over a lot of technical content, so any questions you have are welcome.
And I don't have any questions right now. We do have a comment though when we get to refrigerants about, you know, are we going to talk about the climate impacts from HFC refrigerants and how significant those can be? And I know, you know, we're going to talk about refrigerants and what products have which kind of refrigerants. So maybe we can keep that in the back of our minds to address that a little bit when we come to that part.
Yeah, thanks for that comment. I will touch on that because it's a really important part of the refrigerant you choose.
Yeah. Awesome.
So I guess without question. Oh, sorry, go ahead.
We do have a question. Sorry, we got to give folks a chance, I think, to type them in. Question is, with a code requirement to circulate, where does the circulation return go to in the system?
Yeah, we'll handle that when we talk about the temperature maintenance, which is, yeah, it's a really important function and there's different ways we can handle that. But we'll kind of scratch the surface here, and then there's a lot more resources like DNR's upcoming modules, education modules, as well as the advanced water heating spec that lay out different configurations to handle that recirc return.
Perfect. Looks like we've got another one. This is a great question.
Yeah, that's an awesome question. Yeah, why is it not well known if it's been around for so long? Right, we've had refrigerators for, I don't know, 50 or 60 years, long before I've been here. And we've had air conditioning in our cars, air conditioning in our houses. That's really the same technology, right? It's just moving heat from one place to another. So I don't know if I have a straight answer to that question, because heat pump water heating is a really efficient solution here, and we want as many people to know about it as possible. Yeah, you do need to consider storage tank height to promote stratification. So sometimes you'll see horizontal storage tanks, which will not handle stratification as well because there's not enough height there to be able to handle the separation between hot and cold. So that little layer ends up being a pretty significant volume, that layer between hot and cold. So taller, narrower tanks are better for stratification, and you need to think about the sensor placement, which you can coordinate with your manufacturer, because that sensor that's telling the heat pump when to turn on and off is going to be looking for that change between hot and cold. So the height in the tank is going to be really crucial for the placement of that sensor. And yeah, so I'll move on from here. Definitely just throw some more questions in the chat as they come up, and then I'll pause in a little while here. So now to answer that, where does this hot water return go? We'll talk about the temperature maintenance system. So the goal for temperature maintenance, as I mentioned earlier, is to keep all the water in this distribution loop hot. It gets sent out hot. If none of these fixtures turn on in the loop, this entire line here is just going to go cold. So we have a pump in here that constantly circulates to make sure new, fresh, hot water is entering this loop. And then the water that comes back, it's cooler than the supply, but it's not cold. So the heat pumps don't love heating warm water up to a hot temperature. They like heating cold water. So we're going to handle that separately. And there's a few different configurations that we don't have the time to go into here, but they're definitely worth investigating and talking to the equipment manufacturer, whichever piece of equipment you decide to go with. They'll have a really good insight on which configuration their equipment best pairs with. So you'll see on this slide, we have what's called a swing tank configuration. And on the next slide, we have a parallel loop tank configuration that looks a little different, but we can't dive into that today, but there are resources out there to discuss the differences between those. And the thermostatic mixing valve is a part of this system as well that really provides the same function as it would in any other heating system. It's taking cold water from the city and mixing that in with hot water from your system to supply an appropriate temperature to the residents. We can bump up the storage temperature for greater Legionella prevention and greater storage capacity because we can mix down to a lower temperature that's not going to burn the residents. So it also mixes in some of this hot water return to mix down to the proper temperature as well. So the installation and the design and the sizing of this mixing valve is really important because it's really the last device in a lot of systems that's going to keep your residents from getting burned. So you want to make sure it's installed, maintained, and designed properly for the system at hand. And then the last component we'll talk about in the system is the controls, which is I've seen overlooked on a lot of plan sets, but they're extremely important because they are going to, the controls are what makes sure the tank stays hot so you can always provide the residents with hot water, as well as making sure the heat pumps are running when they're supposed to and they're shut off when they're supposed to as well. If the controls are telling the heat pumps to run when there's already hot water in the tanks, it could cause catastrophic damage for the heat pumps, where a little bit more planning and controls ahead of time could make these heat pumps last much, much longer throughout their life. So there's a couple different configurations you might see when it comes to controls. And one is the internal controls of the heat pump, controlling the entire heat pump and telling it when to turn on and off. And that will be the entirety of the controls in the hot water system, which I've seen work successfully in a lot of different systems. You just need to make sure that the manufacturer is collaborated with and the sequence that these controls are using are considered for your overall system. So get that sequence of operations from the manufacturer and make sure that the temperature sensors are in the right spot to allow these controls to read the right temperatures that they're assuming they're reading. And then the external controls are often a third-party controller that's going to control a lot of different things in the building, but may also control the heat pump water heater. So there's a couple levels of this. One is the external controller can look at the tank temperatures and specifically tell the heat pumps when to turn on and off, which you have to be really careful about because there's a lot of special considerations built in to these internal heat pump controls that might have a conflict with that. So any controllers that are telling your heat pumps exactly when to turn on, those contractors need to be in really close coordination with the manufacturer. And the second, more robust seeming option is the controller just monitors the heat pump. It controls a lot of other things in the building, but the external controller just monitors the heat pumps. And the heat pumps just tell them, okay, I'm running now, I'm making these temperatures, and then the heat pumps are just looking at the tank temperatures and running on their own. And that will allow less conflict between the controls contractor's idea of how the heat pump systems work and the manufacturer's really special oddities built in to the heat pump electronics themselves. So a quick recap looking at, this is a picture of Jackson Apartments in Seattle in the mechanical room. We're looking at the primary heat pumps on the left here, which are going to be feeding these primary storage tanks on the right with hot water. And then that's being sent out to the building and recirculating back to this temperature maintenance tank, which is connected to another heat pump that's not on the screen here. And then there's a controller on the wall here that's monitoring the entire system and the tank temperatures and telling the heat pumps when to run. And that was a premature click, but I think I got in everything I needed to there. So with that, do you have any questions on these different heat pump components?
Yeah, and I'll say, if your head is spinning, welcome to the club, because the first, I don't know, 6 months I was looking at these systems, my head was spinning, and I'm an engineer, so they're complex, and there's something that a lot of folks have never seen before. So Evan, it is, I always love to see those photographs, and it makes it really kind of come to life a little bit. But yeah, if folks are feeling overwhelmed, you should know that Evan and Colin, who presented yesterday, will be presenting more instructor-led courses through Seattle City Light and Lighting Design Lab that delves into the engineering aspects. So feel free to join us for those. That'll help too.
Yeah, yeah, and it's really interesting giving a presentation on the content for heat pump water heaters in 1 hour and trying to hit all these important points, right? So I often catch myself like, okay, I really want to explain this because it's really important. Oh shoot, I just need to scratch the surface though. So yeah, just take notes, be like, okay, so controls are important to think about. Talk to your manufacturer. Just don't forget about them. Look up more resources, which will come through DNR in these deep dives, and then it'll all start making a lot more sense.
Exactly.
Okay, so we have a couple questions here on the components. What is the typical size differential between primary storage tank and temperature maintenance tank? Yeah, the temperature maintenance tank is often a lot smaller than the primary storage because since the temperature maintenance loop is basically a pretty consistent heat loss, we can size the heater to make up for that heat a lot more closely, right? There's not these big peak loads that the primary storage has to handle, or like the primary storage has to handle. It's just a really consistent heat loss. So it's really just sized big enough to offer that, whatever heater you're using, enough buffer so it doesn't cycle on and off really quickly to maintain that temperature. The primary storage is handling these big peak loads, so it's often a lot bigger. And is the maintenance heat pump special due to the short cycle / pressure issues? Yeah, it is going to be special because it has to heat that warm water up to a higher temperature. So you definitely, when you're choosing a heat pump for the temperature maintenance system, you'll definitely want to make sure that that heat pump's designed to handle those conditions. Is there a savings chart / formula or app that can compute the energy bill savings for a resident or small business? I don't have one off the top of my head. That's probably something we can get back with. I dive really deeply into the actual design configurations, but the budget numbers are a little bit out of my playing field, so that's something we could get back with, I'm sure.
I do know Colin spoke to this yesterday, if you were in the Y session, that, I think it's generally you save 2/3 of your energy bill that is focused on your domestic hot water application, right? So it's basically you're plan to save 2/3 of what you would normally spend in energy by using a commercial heat pump water heating system. And I think you said it translated to between 15 and 18% of overall building energy usage that you would save. So it's not quite what you're looking for, but we do have some statistics that kind of speak generally to how much you can save in energy use. So.
Right. Yeah, thanks for bringing that up. Yeah, moving on from here, we can look at the high-level design considerations to think about in these heat pump water heating systems. So the first is going to be heat pump sizing. How big do my heat pumps need to be and how much storage do I need? And then once you know that, we can talk more about the actual selection of the equipment that's available. So talking about sizing, it's really important to take a little extra time on this versus how you might conventionally size a typical gas water heating system as a designer, because we've talked about the need for more storage to handle these peak loads, while the heat pump can be sized much smaller than a boiler in a properly sized system, which is going to bring down your overall project cost, because the price per BTU on these heat pumps make them cost a lot more if you're sizing for that peak load. And so here we can look at the load profiles for different buildings, and this will kind of illustrate why the storage is important versus the heat pump recovery. So this chart right here shows how much an average resident in a multifamily building, how much hot water specifically they're using throughout the day. So hour 0 here we can look at as midnight, and 24 is midnight the next night. So 1 to 4 or 5 in the morning, the building's not hardly using any water. But after 5, everyone starts turning on their showers, cooking breakfast. So a lot more hot water is going to need to be used. So you can see this peak here is almost 4 gallons per person per day. And if you're talking, 500 people in an apartment, that's 2,000 gallons of water in that peak hour. So we don't want to size our heat pump to serve 2,000 gallons per hour, because then it's going to be oversized for the rest of the day. We're going to size our storage to handle most of that load. And then as that load goes down, that's when the heat pump can catch back up and recharge the storage for the next big draw to hit. So everyone takes a shower, cooks breakfast, uses most of the hot water from the storage, and then people stop using water in the heat the heat pumps are recharging the storage until dinner time, when the storage is going to give some of that hot water back up to dinner activities and after dinner showers and things like that. So there's a lot of really good sizing for residential specifically. That's probably the bulk of the heat pump installations to date. So what that sizing is based around, it's not what this profile looks like or how big the peak is. We've already figured that out. It's actually how much water is used throughout the entire day, because that will just scale the size of this graph here. So if we have 100 occupants using 20 gallons a day, that's 2,000 gallons a day in that system that need to be made up by the heat pump every single day. And then there's programs that will say, with your 2,000 gallons a day, we need X amount of storage to handle this peak load that's predictable because it's a multifamily building. And that load changes with different buildings, as you can see on the left here. So if it's a men's dorm, for example, you have this big peak right at the end of the night. And nursing homes, you have a couple of larger peaks in the middle of the day. So that's going to change the ratio of storage you need versus how much heat pump you need to recharge that storage with. So thinking about residential specifically, Ecotope has actually made a sizing calculator that's recognized by the Seattle Code as a legitimate way to size these systems. And what you do is you tell it either the apartment breakdown, like this many 1-bedroom, 2-bedroom, 3-bedroom apartments, or the peak occupancy this building's going to see. And then it assumes a daily hot water usage per person based off a lot of survey and metering data. And then that will give it a total daily hot water usage, right? So here you have occupancy of 60 people, 30 apartment units. Your daily hot water usage is going to be 25 gallons per day per person. And then that gives you 1,500 gallons per day usage. So those are all the inputs, while the output will be, you need 285 gallons of storage paired with 66,000 BTUs of heating. So in an apartment building with 30 units, you wouldn't typically see a boiler with that small of recovery, but we're able to downsize that recovery because we're increasing the storage to handle those peak loads. And then it gives you a recommended swing tank volume as well for one of the configurations of temperature maintenance heating. And we have an element that covers the backup recirc losses as well, which is going to be roughly 100 watts per apartment in recirc heating. So that's kind of a general rule of thumb. Then you can get a lot more detailed than that, but 100 kilowatts, or sorry, 100 watts per apartment of recirc losses is what this is making up. And then so now we've used this program to find how much heat pump capacity we need and how much storage we need. So what do we do with those numbers when we're selecting an actual heat pump? So first we'll look at the available products on the market today. And I say on the market today because this is a very quickly evolving industry at the moment because there's such an increasing demand for heat pump water heaters. So this is what's offered by all the main companies today, but there's going to be a lot of new models coming out in the near future, and there will even be new manufacturers coming out and sending heat pumps from Europe and Japan, where there's more mature markets where heat pumps have already existed for a while. So the most fundamental driver of the capabilities of a heat pump water heater is going to be its refrigerant. I talked about how refrigerant pressure is manipulated to be able to transfer heat efficiently into water, but each different refrigerant has different pressure capabilities it can handle and different pressure requirements to transfer that heat. So we can see in this graph here, we have the air temperature it can handle up top here. So we're looking at CO2. It can handle air temperatures down to -10 degrees. And I have a max of 100 degrees here, but they can tweak that a little bit with different technologies. So refer to the manufacturers for these boundaries, but this is a more general level showing CO2 refrigerant and R410A refrigerants can handle much colder air temperatures, while R134A can bottom out at about 40 degrees Fahrenheit. So if it goes down to freezing cold outside, your R134A heat pump might not work. So that needs to be part of the design discussion. And the solution in Seattle has been to put these R134A units in garages or conditioned spaces that don't go below 40 degrees. And Colin Grist will talk about that in the engineering deep dive and how those garages allow the temperature to not drift below 40 degrees and allow for efficient and reliable operation of these R134A heat pumps. And there's a question about HFCs and their effect on climate change. And so the way that this is measured in refrigerant is called the global warming potential. And that is how well a refrigerant is at heating the atmosphere compared to CO2. So of course, we have these GWP numbers on the side here. Of course, CO2 refrigerant is a 1. It's the benchmark. So R134A, on the other hand, it has a value of 1430. So that means if you release 1 pound of R134A in the atmosphere, it will act as if you released 1,400 pounds of CO2. So that means if there's any leaks in this equipment, then it's much more accelerated global warming potential than if there was a leak in a CO2 water heater. And then R410A, a more conventional refrigerant used in air conditioners and a lot of space heating heat pumps, is at 2,000. So 1 pound of R410 is like releasing 2,000 pounds of CO2 into the atmosphere. So there's going to be there's actually extra code credits that incentivize CO2 in the Seattle code, and more cities are going to be jumping on because of these very high numbers and risks of refrigerant being released into the atmosphere from a leaky heat pump. So if we kind of recategorize the products we saw on the previous slide, we can put them in a few different buckets here. So on the left, you see multi-pass unitary heat pumps, which were originally designed more on the residential side, where you'd put them in garages or basements or some sort of semi-conditioned space that's not going to get as cold as the outdoors. So those are conventionally designed with R134A because it's a really good refrigerant for this multi-pass kind of setup where the entire tank is mixed up, but it doesn't deal with that cold weather well. And then these larger single pass CO2 heat pumps, you'll see the heat pump placed outside, and then it's sending hot water to the tank placed in a mechanical room. They work down to really cold temperatures, and they work really efficiently there. So you can just put them right outside, and they're weather rated as such. And then you'll see Colmac or Nile heat pumps with R134A. These are still a larger split commercial system designed for the outdoors, but they were originally designed for places like Hawaii, where R134A works really well and really efficiently because it's always warm there. So they still can't handle these cold temperatures. So we have to be creative and either install them in warm places or install them in places like parking garages where it can handle that, where it can mediate those lower temperatures. And then once you've decided what refrigerant you're going to use, the general size of your heat pump that makes the most sense for your setup, you have to look at the heating capacity of that heat pump. You don't want to trust any kinds of sales flyers that just have a single capacity listing for a heat pump and a single efficiency, because the capacity varies greatly depending on the air temperature. It's a lot harder to harvest heat out of 20-degree air than it is to harvest heat out of 80-degree air. And most likely that sales flyer that shows your heat pump has a COP of 4, that's going to be measured at this 80-degree air where it really looks good. So, sorry, I thought I messed with my sharing for a second. So if we look at this graph here, what it's showing is the outside air temperature on this bottom axis here, and then the heat pump capacity on the y-axis on the left. So you can see at 60 degrees, this specific heat pump can make 195,000 BTUs. If your temperature is going to get down to 20 degrees in the winter though, you're going to want to design down to this area where it rates at 20 degrees at only 110,000 BTUs. Right, so this is your design point. And then another thing you need to think about is these air source heat pumps, they accumulate ice on their coils, so those will freeze up and require a defrost. So there's going to be a specific defrost rate depending on the heat pump you choose that you need to get from the manufacturer, because if it's rated at 110,000 BTUs, that's likely not including the defrost cycle. So over the course of an hour, it might not be that 110, it might be, say, 80,000 BTUs. So that's the number you want to look for when you're designing for the worst case scenario in these systems. And then so we know the different heat pump manufacturers, how much capacity we have now, and now there's different options to actually bring them to the installation phase, right? The most common I've seen so far is the custom engineered system, where an engineer is specifying which heat pump you need, which storage tank you need, and the configuration they're going to be installed in, and all the ancillary components. But then one step further is going to be the fully specified system, which is going to, a lot more information is going to be provided from the manufacturer or their reps, and they will basically specify for you all of the parts you need for a system that satisfies a specific building. You're still going to have to make a drawings plan set, and it'd be a good idea to talk more candidly with the representative or the manufacturer and see how many of these systems have actually been installed, because there's always strange kinks you have to work through and the first installation of some of these components. And then there's the fully packaged system that has been fully engineered and assembled by the manufacturer, and then that can be installed as one large unit once it gets on site.
So hang tight there just a minute, Evan, because we have a few great questions.
Great.
So about refrigerants. One question that I thought was really just awesome. You know, if, and I'm turning because I'm reading it here from my screen. If
Mhm.
CO2 has a better temperature range and only has 1 unit of CO2 if it leaks, why is it not the predominant refrigerant and why are we using the others?
Yep, that question's been asked many times, actually. And so CO2 is a great refrigerant, and it has some special things you need to consider. But overall, yes, a great refrigerant, and there's a lot more equipment coming out with CO2 as we speak. So I anticipate we'll see that take over the market. They do deal with really crazy high pressures, so you have higher needs for quality control and manufacturing processes that might drive up the price of these systems. So that's something to kind of keep in the back of your head as you're selecting these different systems, is how much more is the CO2 going to cost? There's incentives in Seattle right now that offer more money for CO2 systems because of what you just stated. They're great low GWP and great conditions they can handle. So that's most likely offset in a lot of municipalities, but that's going to be the one thing that might keep them from just completely accelerating past everything else. But yeah, in general, not thinking about cost, CO2 is the way to go.
Okay. So the question, so you've hit on this other question a little bit, which is, you know, is CO2 widely available as a refrigerant at this time? And the answer is yes, it's
Yes.
becoming that way, right? Okay. And here's a question that we had yesterday, and I really think this is interesting. Can systems using high GWP refrigerants be converted to then use low GWP refrigerants at this time? And I'm wondering if that's possible because of this pressure issue with CO2.
Yeah, so none of these conventional refrigerant systems could just be straight converted into CO2, for example, because the pressures are so special with CO2 and different things you need to consider. There are synthetic refrigerants that are not as high of a GWP that are being designed as replacements for 134A and 410A. The trick there, though, is usually those are coming with the design of new heat pump components to handle those. Because if you buy a compressor, for example, to put into a Colmac heat pump, it's going to say R410A on the side, and you're going to run into some issues if you tell a local jurisdiction, well, it says R410A, but I'm going to put this new synthetic refrigerant in it. That's probably going to work just fine, but you'll get hung up with the legislation and some red tape there.
Yeah, maybe some code issues. Yeah. The third part of that question is, what does the future of reducing refrigerant GWP look like? I mean, I know like there's a 513 that's coming out, discussion of propane, other things. What does the future look like, Evan?
Yeah, there's a lot of money being spent on that right now. There's a lot of synthetic mixes. CO2, I don't know if CO2 is ever going to be able to be beat from the standing of a global warming potential. It's a natural refrigerant with a potential of 1. Hopefully, propane will come strongly onto the market as a GWP of 3, I believe, and the characteristics of this 410A, which are really ideal. But we just have to get past the barriers of, the limitation of these flammable refrigerants, which if you think about your barbecuer on the porch that has this big tank of propane or natural gas being pumped into a building at a unlimited rate to heat this water, I think the conversation is worth having. Can we have a little bit of propane in a heat pump on a roof? So hopefully that's where a big part of where these refrigerants will go is things like propane being tested a lot more specifically.
Excellent. Here's another one. Is lower level of quality control needed for high pressure in CO2 also a potential contributing factor to susceptibility, for leakage in other systems? So let me read that again. Is lower level of quality control in comparison to a high pressure CO2 system Also a potential contributing factor to susceptibility for leakage in other systems. I'm not sure if I understand that question, but maybe you're getting the gist.
Yeah, I think so. So I might paraphrase here. I mentioned that CO2 systems are going to need a really high level of quality control to maintain those really high pressures.
Yeah.
But maybe we don't need that kind of quality control for these lower pressures because they have to hold much, it's a lot easier to hold those in, right? That's strictly speaking in terms of the ability to hold pressures. I firmly believe that the quality control on any other heat pump should be just as high. The materials aren't going to have to be as heavy duty because they've been engineered to handle specific pressures. But yeah, that's right. If your overall manufacturing process can be a little, say, sloppier because it doesn't need to handle 2000 psi, there might be a higher chance that you're leaking refrigerant out to the atmosphere. And I think that's going to be really hard to really put your finger on from a market perspective. You're not gonna see any sorts of these standards on marketing brochures saying, well, we kind of build heat pumps well, like only a few of them have leaked.
Right.
So hopefully more studies come out that kind of encapsulate how well these heat pumps are doing and how many leaks are coming out and things like that.
And sure, certainly with high GWP refrigerants being used, you would want high quality control, because if they leak, the damage is so much worse, right?
Yeah, exactly. So it's kind of this cascading effect,
Yeah.
potentially.
Thanks, Evan.
Mm-hmm. Yeah, so these have been great questions that we've kind of gone over time. So I want to be cognizant of that and appreciate you guys coming here. So I'll kind of glaze over the Seattle Energy Code updates, which you shouldn't refer to this presentation anyways to make sure you're code compliant, but it's just kind of to raise your eyebrow on where heat pumps are going. So Seattle Energy Code 2018 is going to be live January of 2022, so in a few months here, and it requires heat pump water heating in multifamily and hotel motel applications. So that's a huge progress for this market, and Seattle's kind of a front runner in this, along with some other West Coast cities. But SDCI, Seattle Department of Construction and Inspections, will be releasing a tip document soon that gives a more high-level view of all the code changes through the Seattle Energy Code that will accommodate heat pump water heaters. So definitely keep an eye out for that. It'll be a really helpful document to point you to the different codes you're going to need to look at if you don't want to go through the Seattle Energy Code line by line. And these are some of the categories that it touches on, being the installation of primary storage, temperature maintenance, and how it interacts with stratified storage, the availability to alarm if there's any sort of system failure, and then what's acceptable for equipment sizing. And then some additional resources here we have a link to is the Seattle Energy Code itself. I've mentioned the advanced water heating specification that now it lists different configurations that these heat pump water heaters have been proven to work well in. And then the EcoSizer, which is the Ecotope's program to size these domestic hot water systems in multifamily buildings. And then maybe, Lauren, I'll let you cover this upcoming training resources from the DNR's perspective, because you guys have done a lot of work and I want to let you show it off.
Yeah, we have. And I'm super excited about we're kind of hitting two parts here. We have some upcoming instructor-led sessions with you, Evan, and with Colin, an engineering deep dive session in October that's really going to get into the weeds of all of the different configurations and different design considerations you should take into account. And then in October, November, design maintenance and operations. And that's a great course. You teach that. It's a great course. Start to finish, what do you do once you decide you want a heat pump all the way down to installing it, all the things you need to consider. It's awesome. But then the other part that's really exciting is that coming in November, we have an entire library of online on-demand commercial heat pump water heating educational modules, and you can see the topics there, but they include 4, maybe 5, if we can get the 5th one done in time, virtual interactive tours. We can go see system installations and read about them, hear about them from videos and different things. You star in some of those, Colin stars in some of those. We have the sizing tool and the manual and the guidelines. We've got the system diagrams and the schematics. We try to answer all of the questions, the available products, even manufacturer training resources and events and different things from the manufacturers themselves are also linked there. So those are coming up. And if you're interested in knowing more about those, please don't hesitate to email me. My email is right there, and I'd love to connect you with how to access those. So those are coming in November. Super excited. Thanks.
Yeah, thanks, Lauren. And this is all the subject of heat pump water heating is the information's been very dynamic, and DNR's done a really great job in keeping updated with how the market's changing and really how all of Ecotope's best design practices are evolving as well. Because as we learn new things through different research, we're constantly coming up with different and more efficient ways to do things. And I think DNR's done a really great job at capturing all of that in this content. So the last thing I'll cover here is a shout out to Seattle City Light and Armando, who was at the very beginning of this. And Armando, I don't know if how tuned in you are, but do you want to cover a few of these things here?
Sure, I'll take a solid 5 seconds just as everyone's can head out. But yeah, very happy to host Colin, Evan, Lauren on these trainings. We've had the why and how over the past 2 days have been very interesting, super amount of good high level information, some detailed engineering information. We're gonna have the recordings for these videos and the handouts on our website, lightingdesignlab.com. If you want to, reach out to us on our email there for any questions. We're going to have the next set of these deliveries October 11th and 13th. So just very excited for that. Just thank you everyone for plugging in.
Great, thanks Armando.
All right, and
sorry, the last thing I'll do is shout out to all of our collaborators as we've gotten this content together, being Seattle City Light and Bonneville Power through their emerging technologies, and the Advanced Water Heating Initiative with a lot of different parties involved there. So thank you for that, and we'll close out with an exit survey that I'll just leave up on the screen here that you can respond through Slido to figure out how we can better tailor all of our content in future sessions and what questions might remain for you that we might be able to hit on.
Great, thanks so much, Evan, and thanks Colin yesterday, and thanks again Armando and Seattle City Light and Lighting Design Lab. We're just very excited to be here, and thanks to everyone who was with us and all the great questions, all the great comments, all the great passion about low global warming refrigerants. Amazing and awesome. We're with you on that. So thanks to everyone. We hope to hear from you through the exit survey, and take care. We'll see you October 11th and 13th, I hope. Thanks, Evan.
Great.
All right.
Thank you. Thanks everyone for coming.
Bye-bye.